In this example, we're going to try to find the volume of a solid revolution, but in this example, we're going to revolve this guy around the y-axis, and so things are going to be slightly different revolving it around the y-axis. So if we're going to revolve it this way, as opposed to the typical x-axis revolution, it's going to look something like this. It's going to rotate around, and so if we draw the mirror image on the opposite side, which is how we typically start by graphing these guys, and we'll enclose the n in like a loop, right, a circular shape. It's not that great. Let me try that again. Okay. Then we'll get this solid of revolution here. If we want, we can do some shading and things like that. But anyway, this is a three-dimensional solid, and the function that we revolved was x squared minus 3. X squared minus 3. So now we need the formula for this guy's volume. Now, if you remember, there was a formula for the volume of a solid of revolution, which you might remember this formula here from some of our earlier videos. V equals pi times the integral from a to b of f of x quantity squared dx. And that seems like the right formula because that's the disk method, of course. However, this is only for if your function is revolved around the x-axis, and ours is not. So that unfortunately is not going to be the right method for us. Here's actually the guy that we need. Here's our formula that's revolved around the y-axis. It's basically the same formula. Only it's got to be a function of y, not a function of x. And the limits of integration from this a to b, some textbooks write c to d. It doesn't matter the letters that you use, just from one constant to another are along the y-axis. The y values are ranging from a to b. So you can see that in the picture here. It has nothing to do with 5. It's from -3 to 22. Right? That's the y value range that we have here. Now, the reason for that is this. If you're revolving your graph around the y-axis, your disk for the disk method are stacked on top of each other as opposed to left to right. So being that they're stacked from top to bottom, they're ranging from -3 to 22. 5 is pretty much irrelevant. So that's the reason for that. Okay, so here we go. Our function is x squared minus 3, and we're going to use this formula here. So give me just a second. I'm going to hide a couple of these layers so we can draw on a fresh layer here. All right, get us a color. Okay, and here we go. So our function was x squared minus 3. And the disk method formula we'll be using is the integral from a to b of quantity g of y squared dy. Okay, so we just basically have to fill in the blanks. So our volume would be pi times the integral. All right, so we need the graph here. I tell you what, I can slide this out of the way so we can see it real quickly. If I move these off to the side, just take a quick little peek at the graph here. What were the y values range for this solid here? Well, we said it earlier. It was -3 to 22. -3 to 22. Okay. So let's move all this stuff back again. All right. And so we'll go from -3 to 22 of some function squared dy. Right now, here's where we have to start being pretty careful with our work here. I cannot use this function because if I wrote x squared minus 3 quantity squared dy, that just doesn't work. This is a function of x, but you can't integrate that with respect to y. It just doesn't work. So here's what we have to do. I have to somehow maintain that same relationship to where y is still x squared minus 3, but write it as a function of y as opposed to a function of x. So that's done just by algebra. We just need to work on this guy a little bit. For instance, you could add 3 to the left-hand side and get y plus 3 equals x squared. Then we could take the square root of both sides and get x equals plus or minus the square root of y plus 3. Now it turns out I don't need the plus and the minus, only the plus is sufficient. What happens is as I revolve this guy, it goes from the plus to the minus and then back to the plus again as it's being sketched out. The minus is the reflection across the y-axis, so I don't actually need that guy. So we'll just take the positive one here. So this is important to recognize. Hopefully you understand this. These two guys here are the same. This guy, our original function, and this relationship, I simply wrote them in a different way. I solved for the other variable. So this is going to be our function of y as opposed to this being our function of x. So we're going to take this out of here now. So let me erase that real quickly. Or take this guy out. I'll get rid of some of this stuff as well. I'll just cut it out and delete it and make it a little quicker. Okay, and we'll pop in that square root of y plus 3 in there because that's our function of y. Compute this algebra and we're done. Nice thing about this problem, the square and the square root cancel, so the volume will be pi times the integral from minus 3 to 22 of y plus 3 dy, and so we'd get pi, integral of y would be y squared over 2, that's the power rule. Integral of 3 would be 3y, bracket with a minus 3 and a 22. Okay, pop those numbers in and that'll be our volume. So let's see, we have we'll have 22 squared over 2. So if you break that down, and you can jot down the scratch work on your paper, that's 22 times 22 over 2. So 22 over 2 is 11, and 11 times 22 would be 242, and then plus 22 times 3 is 66. I'm going to take that quantity and subtract, let's pop in negative 3. Negative 3 squared is 9, so we get 9 halves, and then negative 3 times 3 is minus 9. Okay, so we have those quantities there. Let's take this up here and simplify it. So the volume would be pi. 242 plus 66, that'll be 308. And then minus, and then we have 9 halves minus 9. 9 halves minus 9, that'll be negative 9 halves. And then minus a negative makes plus a 9 halves. And just for simplicity, I'll just go ahead and convert this to a decimal. 9 halves is 4.5. So this would be 312.5 pi. You could approximate that entire thing by a decimal if you wanted to, but in any case, this is the volume of that solid of revolution, 312.5 times pi. So if I hid that layer and hid some of these and bring back the original graph, this guy's volume right here would be 312.5 pi units of volume.